welcome everybody at Metacore, and thanks for supporting us with space and most probably the best catering in Helsinki by Fuga Food. So thank you for that. In this meetup, we will learn about three things: GitOps, platforms engineering, how do we resource optimize in Kubernetes, and a little bit more strange thing called quantum computing with Kubernetes. So these are three very interesting topics. So thanks for our speakers to help us out with talking in the meetup. First, I will do some introduction presentation. Then we will hear from Metacore a bit, and then we will have the presentations. And I will try to be fast. I don't know how many times did you see these intro slides, but this is one of our mission, let's say, to teach everybody about cloud native and CNCF. So I will just run through the presentation and explain a bit what is CNCF, what is cloud native, what is cloud native Nordics, and all of that. So let's start with cloud native Nordics. Cloud native Nordics is basically a community of meetups. We have meetup groups all over the Nordics, and these meetups are collaborating in creating content, and in the past it was even like sharing speakers and all of that. Now it is a bit less active than it was before, but the Finnish, let's say, section is quite actively collaborating from these meetup community. Thanks for the new members. Raise your hand if you are a new member in the meetup community and this is your first meetup. Yeah, cheers for that. Thank you. So, yeah, welcome. Exactly. So we have an almost 2,000 member big community here in Helsinki, and we are trying to organize the meetups every month. And of course, for that we need your help. We need sponsors, we need speakers, and we need organizers. So if you would like to help out, please find any of the organizers. And please, organizers, raise your hand. So this is the gang. Okay, of course you can find us in other forums also. We have a Slack channel, we have an X account, we have YouTube, all of that. Or meetups are live streamed into YouTube, so if you cannot join us, you can see the stream from YouTube, and you can of course watch them later on. As said, we are looking for speakers, but I think it is more effective to talk to the organizers if you would like to talk in one of the events than filing the form. Okay, moving on to CNCF. So all of these cloud native technologies are organized in an open source project called CNCF, and CNCF is a so-called umbrella open source project, which means that it is an open source project which hosts other open source projects. So maybe this is a bit too meta, but that's what it is. CNCF started by Google and a couple of other companies in 2015 with the aim to find a home for Kubernetes, and with the aim to help the development of technologies around cloud native. So the plan was to build different open source projects which are helping the developers to use and influence the cloud native technology with the help of open source by implementing together, therefore making everything more effective in a sense that it's cheaper to do something together than everybody doing it in their own. And of course that also means that it helps reusing the code and let's say develop the philosophy of cloud native. CNCF itself has like a 3-tier project maturity system. They organize their projects into these 3 different tiers. To get into the sandbox tier, it's relatively easy, and projects have just to apply via creating a PR, and the CNCF talk reviews the PRs, and they are deciding if they take the project or not. Getting to incubating is already a bit more difficult than get into CNCF. That's somehow the philosophy of CNCF, is that they are getting almost all projects which have connection to the cloud-native technology, but they filter the projects which are getting to incubating state. And there is an even bigger, let's say, hope to make to graduated projects. So if a project is graduated in CNCF, that means that you can use that in production. It's used by several companies in production, have good community health, and have good support from the industry. All of these projects are listed in the CNCF webpage. There is a projects tab, and you can get the list of the projects in the different graduation levels. It's a lot of projects, and they even have this famous CNCF landscape, which contains, I don't know how many hundreds of projects and different companies and all of that. It is overwhelming, but this is how, let's say, the technology evolves. Like, everybody is free to create a project and build their technology on it. And CNCF, what they call, it's not a kingmaker. So it's not the job of CNCF to select the best runtime. So they will have several runtime projects, and they have several runtime projects, and it's the industry's job practically to select the successful projects. All right. So I was talking a bit about the talk of CNCF. So I will talk a bit more about how CNCF is structured. So CNCF is an open source project which has money, let's say. So it has membership, and companies are paying membership fees. Therefore, they have to have a board. So the governing board is practically a board made from the companies who are paying membership fees, plus the board also has some community members and so on and so on. But the main job of the governing board in an open source foundation, including the CNCF, is to decide on money. This is why CNCF has another organization called the TOC, the Technical Oversight Committee. The job of this committee is to decide on technical things. So this is why the TOC is the organization which reviews the projects if they can jump from one maturity level to another. Also, they decide on quite a lot of things related to how the projects can be developed, what kind of support do they get, what is the, let's say, the developer experience and all of that. All of this, like everything related to technology is in the hands of the TOC. And there is a third organization, which is the end user committee, and the job of the end user, the job of the end user committee is to get end user feedback, basically back to the communities. And on top of that, there's a marketing committee, of course, working on the marketing of the projects and CNCF. And there are different special interest groups which are dealing with, let's say, different domains. Like, and it's not special. It's what is it now? Is it 6? Anyways, so it's about different domains. There is a sustainability tag. It's tags. What is tag? I don't know.
Technical advisory group.
Exactly. So they renamed 6 to tags. Yes. CNCF also works on creating tech radars, which means that they are trying to put the different technologies into different, let's say, maturity level, like what companies should do with these different technologies and projects. Should you just assess them? Should you try them? Should you adopt them? And they are doing these technology radars for different technology domains. So that's, let's say, a service from CNCF to help users to figure out what to do with all of these projects. CNCF also provides you a cloud-native trail map, which means that it gives you some kind of a roadmap. How can you adopt this technology? I think it's not that important anymore. It was more important when everybody just started their cloud-native journey and we just didn't know how to do all of these things. Now all of us know how to do all of these things. Not. Okay, then some words about the philosophy of cloud native. What do we mean when we think about cloud native? Is it containers? Yes and no. It's not only about containers. So if you containerize something, it will not be cloud native by default. It's not even cloud. Like if you put something into the cloud, it will not be cloud native. It is more like a paradigm. How do you develop applications? How do you develop or how do you run them in an infrastructure? It's more like about open interfaces and how do you handle APIs. So it's more about a philosophy how to build applications than any particular technology in the stack. And this is what CNCF tries to help you to understand, and this is why, for example, there are lots of projects in CNCF which are not actual runnable components, but defining some kind of an interface for some purpose, to provide some kind of an abstraction or some pluggable or plug-in interface for something like CNI, CSI. All of these interfaces are defined in CNCF, and the aim is to create a pluggable infrastructure for your needs. Also, it's a common, let's say, misconception that Kubernetes is a platform. It is not. It is a platform to build platforms, or I could even make it more generic. According to my understanding, Kubernetes is a generic orchestration framework which was originally built to orchestrate containers, but it can orchestrate practically anything. So and being cloud native means that you recognize this kind of possibility in Kubernetes and you start to use Kubernetes to orchestrate everything which is around your application. And with this, I hand over to hear about the committee and the trainings. Thank you.
Yeah, so there are many certificates and training programs around CNCF that you can go through those and start your learning process. And there are a couple of different certificates which you can certify yourself, and there are different ones starting from Certified Kubernetes Administrator, CKA. Then there is one for application developer, which is called CKAD, for security specialist and security associate, and Kubernetes and Cloud Native Associate exam, which is a bit like beginner level. If you want to start from somewhere very beginner level, you should start from here and then go through those administrator levels. And then there is a new thing in CNCF with 5 cool certificates. You get the Cube Astronaut certified. I think they even give you some blue coats. So it's a cool thing. There are other certificates in CNCF which are not specifically about Kubernetes, like for Argo, for GitOps, service meshes, and also they have many different courses. Like it's not just about certificates. You can just take courses and have some learning about different topics which are available in the CNCF. Then a few words about community, how you can collaborate or reach out to the community. First of all, you can meet the ambassadors in each region. There is a link here in the slides if you want to take a look. There is mentorship programs which you can register. You can fill an application and be part of these mentorship programs. There are cloud native community groups which they hold the local events such as us. There are Kubernetes community days. These are like a smaller scope of actual KubeCon. KubeCon is the regional event which is yearly, once in Europe, once in US. But the community days are smaller scoped events which are in different countries, and you can participate, you can send your talk proposals, things like that. So these are all different ways that you can get involved in the community. And the next KubeCon is in November, Utah, in the North America. If you are willing, you can register. I think the registration should be still open.
Yes.
Yeah.
You can even fly in and just walk in the door, unless it's
If you have enough money.
outsold.
Yeah.
Yes. Yes, have to have a big credit card.
Yeah. But yeah, as I said, there are also KCD events happening all around the world in different cities, different countries, and these are also a good place to start if you are thinking of submitting some talk proposals, for example. These are many different ways that you can reach out to us. You will find all the links in the slides. I'm not going to go through this. And with this, I think we are done. Yeah. You want to?
Yeah, we have previews from that. So.
Okay.
For coming. My name is Syrjänen. I'm CTO of Metacore. So the next couple of minutes, I'll be talking a little bit about Metacore and what we're doing here. So quick question first, who liked the burgers? All right. So you can all thank Marita. She's there at the end. She was the one organizing this, and thank you so much. And she's hiding. Who didn't like the burgers? Okay, cool. Just wondering. All right, so a bit of a welcome from Metacore. Really happy that you're all here. For those who never heard about us, we have a saying here that we are the gaming company that where players are the closest to our boss. I joined 7 months ago, so it's been quite recent for me. And let me tell you that it's my first gaming company, so I never worked in gaming. I never worked for Finnish companies. Also, I'm based in Berlin. I worked for many different industries and e-commerce and food delivery. And when Mika, the CEO, told me this, I didn't believe him. I was like, yeah, nice thing to say to people. And then I joined, and it turns out that the reality and the culture that the company has is quite remarkable, and it's really true. Don't know what happened here.
Black screen.
No, we're back, right? We have a mission to entertain hundreds of millions of people for decades. So we develop mobile games, casual games. Our biggest success is Merge Mansion. You probably heard about it, and if you didn't, well, now you did. You can also give it a go and try. And we want to build a portfolio of games, right? I mean, right now we only have one game that is actually out there. We've been developing many other things and trying out and learning from that. And the goal is that we'll develop more games that you could play. gaming company based here in Berlin, offices in Berlin since the beginning of the year. We're roughly around 250 people. Merge mentioned that is the successful game, as I mentioned, has more than 50 million downloads over the course of 4 years, right? So, and yes, we want to build much more than just one mobile game. A couple of numbers that people are always interested to know what's going on. So our revenue from last year was roughly around 162 million, a growth of 26% from the previous year. Our team is rough, I don't know the exact number, probably our recruitment team knows, but it's 240, 250. We did have some funding raised for 150 million, and our engagement score, so that we evaluate every month, Angel in the company is 85 out of 100, right? So, Merge mentioned got a lot of attention in the media for the game that it is and for the story that it tells, for the characters that he has, and also a couple of campaigns and marketing campaigns that we had. It's very interesting. I can also tell you that I didn't know Metacore before, but my wife knew Metacore before because she was playing Merge Mention, and she was all excited when I said that I was talking with this company. And I think it's always because she was always entertained by the story. And then we did a campaign with this fellow here. You probably saw him, Pedro Pascal. We did this campaign right after he filmed the first season of The Last of Us, and after the end of the third season of The Mandalorian. So we got him probably at the peak of one of the peaks of his career, most likely, right, in terms of fame. And he was very excited doing all the marketing campaign with us, and it became quite interesting and very. You probably saw even the advertising a little bit in social media, etc. Right, so a lot of good news also about it and the story and how the campaign was. Yes, just a few more things. It's really, and I know that you probably think, well, you're just saying that because you work for Metacore, but it's been definitely one of the best experience, if not the best experience that I had professionally. I work with great people, really talented people. I embrace the Finnish culture a lot with the 4 weeks vacation that people have here, even though I didn't took it, but I really recognize that it's great. And it's really a great place to be working. Yes?
Can you speak to the microphone because I can't hear anything?
Okay, sorry. Better?
Yeah.
All right. And it's definitely like a culture of trust, and I'll let Juho also, when he presents, maybe he can talk about a lot about that. Autonomy, psychological safety, and well-being, right? I mean, it's a company that really, we work hard to make sure that people are happy and that our players are happy, yeah? One thing that I'd like to still share is that these are our 5 values. It's quite recent that we also introduced this. We had our cultural agreement that is also public, and you can see it on our website. And these are the 5 values that we live very intensively, I would say. All right, and that's pretty much it, right? So if you have any questions, I'll be happy to answer. We'll be around. Don't worry, there's more burgers, right? Don't worry, there's also much more deeper and more interesting conversations and presentations that are going to follow. And once again, thank you so much for organizing this here. It's a pleasure to be here and to receive you all here, and enjoy the rest of the event. Thank you. Juho.
Hello. Hello and welcome from me as well. My name is Juho Syrjänen. I'm a platform engineer here at Metacore's infrastructure team. We're a small team of 5 engineers. We're responsible of keeping these nice games we have live. We try our best. You'll learn more of what we do in the coming talk. So let's go. What's happening? First and foremost, I'll talk a little bit about our internal developer platform, how we got here, the issues we had so far, and how are we doing thus far. Throughout this presentation, you'll be hearing a lot about this lighthouse. That is the name of our developer platform. It has 3 core building blocks. Terraform, of course. We need to make our infrastructure somewhat present in AWS, so we use a lot of Terraform to provision infrastructure, just as like EKS and compute resources, VPN, whatever. We have a centralized repository for that does everything. We have tried to separate it a little bit for IAM roles and policies just to be a little bit safer. So yeah, EKS, very vanilla EKS. We don't really do anything else than just deploy the cluster and then leave it for the cluster add-ons, which is the beef of this presentation. So we have one centralized add-on repository which deploys everything that happens in our cluster. It's a monorepo. It's getting bigger and bigger by the day. We use Customize and Helm to manage all of our cluster add-ons. And what deploys them actually is Argo CD. That's essentially what I'll be talking to you about today, as well as this environment promotion process, which is also a topic today. The topic is, as you heard, GitOps first, but we still do a little bit of CI, such as automated deployments of Terraform. I guess that is still CI/CD, but anyway, CI is test and linting and code conformance, which happens as well on the background. Now, so Lighthouse. We started developing Lighthouse around 1 year ago, maybe, and before we did anything, we decided to put a few principles into the board. So, as I said, we're a team of 5 engineers, small team. We want to automate as much as possible. So, of course, that is our first tenet. We want to be efficient in running our workloads. We want to be cost conscious, as Sergio always tells us. So, workloads need to be efficient as possible. We want to expand our clusters and have the platform to be as changeable as possible. Especially here in the CNCF world, everything is constantly changing, right? We don't want to really lock ourselves in. We want to develop a platform that is future-proof, so to say. All right. Well, it might come back. Next tenet is reliability and resilience. As you've heard, 50 million downloads all over the world. Need to keep those games live and the players happy. So we build to expect failure, and we try to build for resiliency. Scalability as well sort of leaps towards the efficiency. We want to scale in meaningful ways. Whenever we launch a game event, we want to be able to sort of predict a little bit, use Keda and things like this. It's a new and upcoming feature in our platform. Principle of least privileges, of course, in the core. And we try to build everything in a multi-tenant way, so we can actually host many different applications in our clusters. So, in the heart of everything still is Argo CD. This little guy here, this lighthouse, that's our icon, very cute. Courtesy of Midjourney, if I recall correctly, so well, might change at some point, but yeah, he's very cute and he really likes Argo, they're best buddies. So, how we got here? As I said, we put these principles on the board and started building. We provisioned the cluster with Terraform. We started to use Helm and Customize to deploy add-ons, such as, well, we figured we might need an ingress controller. I guess our games are public. They might need some secrets. They might need certificates. We put Cert Manager, external secrets and everything into repo and started publishing this to the cluster with GitHub Actions. So, very soon, we started noticing things just failing in our pipelines. Here you can see we are having four clusters here now, and things just fail at some point. The nature of CI/CD pipelines is these are sequential; they run in order. Something breaks in the middle, that's not good. A lot of things just don't happen then. Especially this guy in the right-hand side, Velero, causing us a ton of problems. Backup tool, if you don't know what that does. So we started noticing that even with these 5 or 4 clusters, the pipelines don't really scale. How about when we have 15 clusters or 50 clusters, right? We could probably make them scale, right? Like you can do anything, but it's YAML engineering. We are 5 little engineers with limited time, with limited resources. We still need to keep the games running while we develop this. Maybe not the best place to put our resources in. The other thing with CI/CD pipeline that really bugged us is that they always run on demand, right? It's rather hard to go and remedy issues that happen in your clusters automatically with CI/CD pipelines. You could probably set up some watcher in your cluster and set up a webhook that reports to GitHub to start the action whenever things hit the fan. But again, more work and not that much difference than perhaps some other options. So, will GitOps help? By the way, if Jair is watching, thank you for this meme. So we started asking this question: will GitOps help? And the answer for that, of course, being well. Maybe. So, well, can't be sure before you try, right? So we started trying. And if anyone has ever worked with GitOps, you most likely hit this first bullet point right here. How do you structure a repository, right? We have 5 clusters at this point. And how do you structure a repository to support multiple unique configurations? Our unique configurations were essentially ARNs and naming conventions in our host names and things like this. And how do we minimize code duplication? One of our principles is keeping it dry. We don't want the configuration to become wet. Don't repeat yourself. So a big question in the GitOps world. You could of course do it with Argo CD Vault plugin. So what Vault plugin does is it actually integrates with some secret managers and parameter stores, and you can inject shit into your YAML with Argo plugin during the rendering phase. Works quite well. Very big topic in the Argo world. People like it or they don't. Or you can have environment-specific config files. And then how do we handle environment promotion? So we don't want all the commits that we commit to main go directly to production environments. We want to make sure that when we release software, we do it in a controlled manner, especially when we have production workloads and, for example, stateful application. We don't want to just take out nodes under them at some point. So rotations and things like this need to be thought of. We always want to release gradually and have everything tested properly and have a nice little release flow from dev staging to production, right? So traditional challenges with GitOps. Okay, every time I sort of kick this, maybe I should take some distance. Okay, is it back? So.
Or maybe I just need to buy a new cable. It might also be.
Both are budget things, right? So repo structure. Okay, this is looks very confusing on the left-hand side. This is our old repo structure, right? So we have a cluster name here on the very root of the repo, and under there we have our little add-ons. So cert manager, EVS drivers, DNS, whatever. And this you can see, this is very wet. We repeat ourselves a lot here. All these things are duplicate, and whenever we have 50 clusters here, there's a lot of things we have that is exactly the same, and it's really annoying to manage. So we started this process of starting to restruct the whole thing. So we moved towards the right, and what we did is we moved these little add-ons here to the very root of the repository, and instead of having everything under there and duplicated, we just have one thing. The Helm bit is the beef, so the purple thing here. So instead of having all this duplicate, we just have one chart.yaml definition. This is our own custom chart.yaml definition. It is referenced in the upstream of the Helm chart. So for example, cert manager, it goes to, I guess it's in the 6th store now, and it referenced there and sets the version number there. And then we have a lot of these values files. So the common values file is the value that is always common. So every single cluster shares this. And then we have our specific values under these environment values files. This way we can really reduce the code duplication, and even though we still have a lot of different files, it is much nicer to manage this way. In the values files, for example, in the Lighthouse dev values file, we just have 3 lines of YAML instead of the common one has like maybe 100. So a lot less of duplication instead of just having it all in the left-hand side every time. Then there's the customized directory. Sometimes, most of you probably know, working with Helm, these charts might lack something. for example, Cert Manager has alerts, but they don't really alert you if your certificates are expiring at certain times. So we want to be maybe a little bit more in control. So we add this customized patch to add some extra things. And another good example is service monitors, which are quite often missing from the Helm definitions. So what happens then? We have our cool new repo. There's a new commit that hits the main branch. Argo is always looking at the Git repo, and the renderer starts to work. So there's the repo server. It syncs with the Git repository, and then there's the application controller that does the actual work. So Argo does a few things depending on what plugins you give it. In our case, we give it the Helm plugin and the customized plugin. It runs Helm template and customized build and spits out a YAML file. That YAML file is then put into Kubernetes. Now, how does this happen? It happens with this cool thing called application set. Right, this is my favorite thing in the world. So, on the right-hand side, you can see an actual application set. This is our sandbox clusters applications. It's just some values I've taken out that are a bit sensitive. But in the generator bit, you can see that we are using this application feature called Git generator. So what it actually does, it reads through your whole repo folder tree or directory tree and indexes it into a map array. So what we can now do, we can use this path.segments bit to reference to our repository directories. So if we go down a little bit further here, maybe my mouse is showing, yes, into the template.metadata.name, we can see that we are giving it our cluster name, so our sandbox cluster, and then the 0 index of this path segment. Now, what happens, you saw before on the very root of our repository, the cert manager is on the root. So this actually loops through the whole repo and injects that value here. Then you can see in the spec, we give it a destination, again, the same index. It is the cert manager, so we are putting it into the cert manager namespace, and the server is the EKS cluster address. Then in the sources, we again give it the repo URL and the branch, and then the path. And there you can see this starts to make a little bit more sense. We're giving it two value files, the common one and the sandbox values. So when we do a kubectl apply and apply this application set to our Argo cluster, this happens. So this is a screen capture from Argo CD, and you can see that it has gone through the whole repository and added these nice applications to our platform. And it's rather small, but here you can perhaps see that the target revision is sandbox, and the namespace is cert manager, and so on and so forth. And for the other ones, the namespace is external DNS and so on. So it works rather nicely, and everything happens automatically. So whenever we want to add a new add-on to our platform, we don't have to touch the application set at all. We just add that same folder into our Git repo. Argo CD will automatically pick it up and deploy it. Now we start to scale this up, so not just the sandbox. There happens to be now maybe 3 application sets. We can all do this via the Argo CD application set. So things start to scale, so to say. So in our case, we have 2 Argo CD deployments. We have one for our sandbox thingies and one for the actual workloads, and then this sync between our clusters. The lighthouse platform starts to take shape, so to say. But how do we deliver this then? We have our cool repo, we have everything in our main branch, whatever, and our application sets are syncing all the time to our production clusters. It starts to be a bit chaotic. New pull request goes to main, and it starts to sync with the production environment. Suddenly, production nodes are rotated, our stateful workloads rotate, we lose some data, not good. So there are a few options we have considered. We could, instead of having branches, we could just make the target revision point to main, turn off the Argo CD autosync, and use Argo CD CLI to sync the applications in the GitOps workflows. Probably works, but doesn't scale that well. We could, of course, split the monorepo into cluster repos. again, probably works, but with 50 different clusters, probably not. We could also keep the old directory structure and release everything to main and target the directories with our pull requests. Again, yeah, but I want to be more elegant. We could just YOLO it. Might work, might not. But what we actually did is environment promotion. So the thing, what we wanted to achieve is this, that every commit that hits our main branch should eventually reach all clusters. We want to have a promotion flow from dev to staging to production, so we test all of our changes in these clusters. We want to only release the tested and verified changes, and all of these environments should not have any drift between each other. So we don't want to have release 1.2 in prod and 1.5 in staging. We kind of want to keep them all more or less the same. We also want to create a process that doesn't hinder our cool agile development ways. We want to be fast. We still want to do releases daily, and we don't want to be hindered by any process. We don't like the word process, right? Even though this is a cool process. The release must be completely automated as well. We don't want to have to click around too much. At least we hope to do that. And unnecessary complexity should be avoided. So here's what we did. Flowchart, everyone likes those. We did branch-based environments with protected branches. So some of you who have been drinking the Kool-Aid of the DevOps world, such as myself, have most likely been told that branch-based environment is a bad thing. And I used to agree with that, and maybe, well, I'm still on the fence, but we tried to make it less bad. We do the release automation with semantic release, and to create influence by the CNCF project's way of releasing software, as well as trunk-based development. And also, there's a very good topic and talk in the this year's Argo comp by Kostis from CodeFresh. Very cool guy, likes to talk about this. But I'll go through the flowchart real quickly with you guys. So let's say new add-on, introducing X, comes to our add-on repository, starts to wants to be part of our cool new platform. It's ready for review, and we say, okay, LGTM, and give it a thumbs up and approve it. It gets merged to main, instantly synced with Lighthouse dev cluster. So our dev cluster is sort of our rolling release cluster. So developers use it for testing, we use it for testing. It's always on the bleeding edge of our release flow. Once this is released to main, we run our CI, so tests, whatnot. If those pass, we trigger the actual release. So semantic release looks at the commit syntax. If it's has a certain scope, it will bump up the semantic release semantic number up. So this is being a feed, so it will do a minor version release, so 1.1 is created. Now this is marked as a release candidate. We can say that this is a dev pre-release in our process as well. So we use this whenever there's maybe we know that there's a few pull requests coming, we want to bundle them together, right? But normally it just goes forward. So the next phase is we trigger a release workflow, and what this does is there's automation within our GitHub that just creates a bunch of pull requests. All of these pull requests are targeting one cluster, and they are targeting the branch of that cluster. So for example, here you can see that this release pull request is targeting our staging cluster, and again, things happen, linting, code conformance, blah, 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 and gets merged to staging, and instantly syncs to the staging cluster with Argo. Now, at this point we say, okay, stable release, again, we let our customers prepare their workloads for the prod release, and then we trigger it out, boop, it's in prod. So all this happens quite automatically, and well, we are not afraid, we don't need to roll back, we just do another release then. But this is essentially what happens, right? And I have a little example here. Here's one of our releases just happened. You can see that Argo CD is doing a lot of syncing here. So by Argo, what it means when Argo does syncs, it actually changes something in the software that it's managing. All right, that's about it. Yesterday, when I was finishing up these slides, I was asking our users some testimonials, so you guys know this actually is working and it's nice. So here it goes. I got this from a backend programmer, so it's clear that the info team is trying their best. Yes. One of our lead game developers was left speechless. No? Our lead tools developer said that his family died, but he's okay. He's using Lighthouse. That's very nice. And one DevOps engineer said that their idea of optimizing means ensuring our servers are always at 100% CPU usage. So again, tying up to our principles of the platform being very well utilized and being yes, exactly, yes. Well, that's it. That's Lighthouse. Thank you. Thank you. Before I wrap it up, I would like to let you know that we are recruiting. metacoregames.com/careers. If you like this, join our team. If you don't like it, join our team and fix it. There's also a lot of cool programmer jobs available, so please give it a look, and thank you for coming. Cool. Who's next?
In one of its particular branches, they are all protected so that nobody can move to them. It just all goes through the pull request flow. But how many times have you had a case where you had to manually fill in that?
Yeah, good question. So, how many times have we had ninja commits to our protected branches? And the answer to that is sometimes. And we do have some issues still when we refactored the whole repository, that there might be some merge conflicts. We try to resolve them, and now that we've been having this live for a little while, those merge conflicts start to go away. But yeah, there is git blame, git log. If someone does that, they will know. And we try to disencourage that for sure. But yeah, not often, but it might happen. We are not that perfect yet. Any other questions? Yes.
So you said that you started working on Lighthouse about a year ago. You worked a lot of fancy high-level goals on it. What's your realistic assessment? How far are you towards those goals?
Well, as one of our testimonials said, it is clear that we are doing our best, and we are quite close, I would say. We started developing Lighthouse with these goals in mind, and we do have a lot of, well, not a lot, but we do have production usage, and we try to stay within our principles. So I would say we are maybe, let's say, I have some of my colleagues there in the audience, I would say we're 75% there. Any objections from the back row? Thumbs up, we got a thumbs up. Yes.
We'll take that.
Yes. Any other questions? Yes.
I can just sound
Okay, I can repeat it, yeah.
So how do you handle like a dependency with a component? For example, some components need to be deployed first in order to have some, like, let's say, non-staff, like the production
Yeah.
especially. Like, how do you handle? Is it R2C doing that, like that kind of dependency? Okay, this component goes first, and then this.
Yeah. So I would say there are probably two big blockers. One is the CNI, another one is core DNS. So these applications need to be most likely available before anything else can happen. So what the application set does, it starts everything at the same time. So things keep failing until those happen. So let's say there is no CNI in place before ingress controller. The ingress controller is just failing until that happens. So in case we are bootstrapping a cluster directly from nothing, so Argo CD can handle that quite well. And the question now is, what manages Argo CD? So, the answer for that is Argo CD. So, yes, yeah, it's a chicken and egg sort of a situation. Yeah. So the initial Argo CD deployment was probably kubectl apply from my laptop. So yeah, well, now it's managing itself, but in a case it completely destroys itself, we would have to run our DR exercises, which we do run quarterly. Hope that answered some of your, yes. All right. Any other questions? If you're too shy to ask now, please just come and talk to me after the presentation, so let's have a chat. All right, thank you.
right, I think we can start. I hope you can hear me clearly. If not, just let me know. Good. Hello everyone, my name is Feruzjon. I work for Intel, and today I wanted to talk about how can we optimize the resource consumption in Kubernetes. The project that I'm going to touch today has been already talked about that in the previous Kubernetes Finland meetups and then in the Kubernetes talks. But then there have been some new features that we added recently, and then I just wanted to show some demos, some potential usage, and maybe it will also suit you in your Kubernetes clusters. All right, before we talk about how do we optimize the resources in Kubernetes, I just wanted to start from the history about how the CPU and then how the memory is organized in our processors. And then just to start with, I just wanted to talk about unified memory access. Probably all of you know what it is. It's a little bit of history. Nowadays we're talking about NUMA, or non-unified memory access, but before that we had unified memory access in the, let's say, in the CPU architecture. So usually before the NUMA, how the CPU would look like is that, or the architecture of the processor would look like is that you have, let's say, a bunch of CPUs, and then you have some memories in your machine or in the server. And then if the CPU want to talk to the memory, it had to travel through the memory controller, and then the speed or the bandwidth of the talking from the CPU to the memory would be the same for all the CPUs. So there was like kind of centralized memory unit for all the CPUs, and it was very slow for the latency sensitive applications. And then because of that, there was a kind of improved version of this memory access, which is called nowadays NUMA, or the non-unified memory access. So in the non-unified memory access, what happened is that, so nowadays for each CPU, let's say, it's not all the time, but we can just say one example. For the CPU, you have memory which is pretty close to that, and this memory that is close to a particular CPU is called local memory. So if the CPU wants to access to the memory, the time it takes from this CPU, CPU1, to this memory is very short compared to CPU1 talking to the CPU on the other corner. Of course, every CPU is allowed to access to every memory on the node, but then it makes sense and it's efficient to talk to the memory that is closer to the CPU. So that was the idea of the NUMA architecture. And this is not related to Kubernetes, but it's in general how the CPUs and then the memories were organized nowadays. As I say, just imagine that you have one single server, or the machine, or the Kubernetes node, doesn't really matter. At the low level, you have, let's say, 16 cores. Out of the 16 cores, let's say they are divided into two kind of virtual groups. Each group is called NUMA node. So in this case, for example, imagine that we have two NUMA nodes, NUMA 0 and then NUMA 1. Every NUMA has 8 cores, and then every NUMA has its local memory. So if any of these CPUs want to talk to the local memory, of course it's faster compared to, as I said, talking to the memory that is on the other side of on the other NUMA node. Now, coming back to Kubernetes world, imagine you have local Kubernetes cluster or the on-prem, and then you have, let's say, one single Kubernetes node. And then in that node you have 16 cores in total. So from the point of the Kubernetes, all the CPU cores and all the memory, it's like a shared pool. So basically Kubernetes assumes that everything is just one big box, and then everyone is free to share or consume the CPUs and the memory in the Kubernetes world. And imagine you have some pods. First, by default, you have like kubesystem pods, then you deploy some application, then you deploy another application, then you deploy another application. What happens is that every application is free to use any of the CPUs by default in Kubernetes. So that means there could be some cases that multiple applications will be consuming some parts of the same CPU. For example, up1 and up2 at the same time is consuming the CPU number 7. At the same time, up2 and up3 is consuming 11, and so on. So this might not be a problem for some cases. In some cases, it is a problem. So it is a problem, for example, when your application is latency sensitive or the bandwidth sensitive, or you've probably heard about noisy neighbor problem in the Kubernetes context. So sometimes you want to isolate your application as much as possible so that nobody else is using your CPUs, only your application, which is very critical for you. But how do we do that in Kubernetes? By default, Kubernetes, as I said, it's assuming that it's a shared pool of CPU and memory and everyone can use it. And we earlier talked about the NUMA. So we actually have this NUMA architecture in the hardware level, but then we're not using it in Kubernetes. Can we actually use it in Kubernetes? So if we wanted to use it in Kubernetes, if you look at the architecture, let's say, of this node, which is like assumption. So imagine that you have 4 NUMA nodes on this node. So every NUMA node, well, you can forget about the socket. This is actually a mistake. But every NUMA node has certain amount of CPUs. In this case, it's 4 CPU cores or 4 logical CPUs. And every NUMA node has some local memory. So now if you try to imagine that all of these applications that you had previously, they are critical. So very important that you want to isolate them as much as possible from the other applications that are running on your Kubernetes cluster. So it would be nice if we could actually divide all the CPUs into 4 kind of different decoupled rooms, or the NUMA nodes, and then put up applications only on specific NUMA node without crossing the boundaries between these NUMA nodes. So this NUMA architecture is available on the host, on the server, but it's not exposed to the Kubernetes. So now if you look at, just imagine again that you have one server, or like a machine. First you have the kernel. On top of the kernel you have some low-level container runtime like Kata or gvisor or runc or crun. Then on top of that you have normally high-level container runtimes, which are like containerd and cryo. And then you have the kubelet, and then the kubelet is basically managing your applications or your pods. So when you create a pod, it's actually kubelet who is kind of initially responsible for managing it, and then it's sending a request from top to bottom, and all the way it's ending up on your hardware, consuming some CPUs and the memories and other resources that are available. But then this server has actually architecture similar to this, just imagine. So you have one big system which is divided into 2 sockets. Then every socket has, in this case, 2 dies. Every die is owning 2 cores. So if you basically place your workload, let's say you have a pod that requires 2 CPUs, CPU cores rather, it would be nice to place those workloads somewhere here instead of consuming 1 core from here and 1 core from here. Why? Because if you're accessing the memory, then this core needs to access the memory maybe somewhere here, so it will it will take a lot of time in terms of the latency. But then if you use only these 2 cores, there's a high chance that you have this memory somewhere close here, and then it takes less time for the CPU to access the memory. But then we understand that this is the architecture of the server, but it's not visible to the Kubernetes. So how do we do that? So we need something that can expose our architecture to the Kubernetes level. So what we need to do is that first, inside of Kubernetes, we have to build a topology tree. So we have to get the understanding of how the hardware looks like. Then we have to, once we analyze or once we build the tree, we have to expose it to the Kubernetes. And so once we have it in the Kubernetes, then when we're placing the workload or when you're creating your deployments or the pods, whatever, then you have to make the decision about the placement of those workloads based on the tree of your server, so that you place them as optimally as possible. As I said, by default, it's not possible in Kubernetes, but there are some projects, and the project that I'm going to talk about is NRI, or some plugins of the NRI. So for those of you who don't know about NRI is yet another interface similar to other interfaces in Kubernetes. So you have the CRI, you have the CDI, so there are a bunch of interfaces, and the NRI is relatively new. So what NRI is like, compared to other interfaces in Kubernetes, it is not baked into the Kubernetes itself. It is coming with the container runtimes. So when you're running, when you're using containerd or cryo, chances are that you already have the NRI. In some of the versions, NRI is not enabled by default, but soon, if I'm not wrong, for the containerd 2.0, from the containerd version 2, it's going to be enabled by default, and soon will be for the cryo as well. But then, if it's not enabled, you have to enable it manually, or there are some automated ways actually to do it. So, but what is NRI? So, imagine the case that you're creating or you're sending a request to create a pod with any client. The pod creation request goes to the kubelet first. And what kubelet does is that it creates a CRI request because the request is going through the CRI interface to the container runtime. It creates the CRI request and sends it to the container runtime. In this case, the first runtime is a high-level container runtime, like containerd or cryo. Usually, without NRI, what would happen is that the request would just continue from the container runtime to the low-level runtime, as we saw earlier. The only thing what, in this case, runtime does is that it just translates the CRI request into the OCA spec and sends it down to the low-level runtime, and then the runtime is actually ending up creating the pod or the container in this case. But when you have the NRI, we just intercept the traffic here, or the request, within the container runtime, because I said that NRI is within the container runtime. So container runtime has this piece, NRI, it's called Node Resource Interface. In this case, CRI request is passed down to the NRI, which is modifying your OCA spec. NRI by itself doesn't actually modify the OCA spec. It is actually kind of like the endpoint into which you can plug your own custom logic. In this case, custom logic is called plugin. So let's imagine that we have some plugin which is plugged into the NRI. So the request is passed down to the NRI. Plugin is based on its logic doing some modifications into the OCA spec, modifying some parts of the OCA spec, some resources or some labels, some annotations, whatever. And then after the modification, it sends it back to the NRI, and then from there it just continues again to the low-level runtime. And what happens is that, so your initial request is modified according to the logic of your plugin. Anyone is free to develop plugin. There are some open source plugins. There is a project called NRI plugins, I will show later, which is a collection of the NRI plugins. You can actually come up with different ideas what you want to develop in this plugin. It could be some resource optimization related plugin, it could be some device injection related, some other hooks and so on. So you can just be creative. There are limits, of course, about what you can and what you cannot do. There are some security concerns, but in general it's quite powerful interface that allows you to basically modify the OCA spec. And one of these plugins is called Balloons plugin. And this is something that I'm going to talk right now and then show the demo hopefully by the end of these slides. So how does Balloons plugin work and what is it doing actually? So at this point, imagine you have the Kubernetes cluster, let's say running on containerd, NRI is enabled, and you are about to deploy the Balloons NRI plugin. So when you deploy the plugin, it's actually zero config plugin by default. So even if you don't modify the plugin or you don't pass any configurations, it's already by default optimizing your workloads so that efficiency is taken into account. But then of course it's quite powerful. There are a bunch of options that you can tune and then optimize based on your needs. But then imagine that you're using the zero configurations, you're not modifying anything, but just deploying the Balloons plugin. What happens is that according to, or from the view of the Balloons plugin, it is basically, let's say in this case, creating 3 different balloons. Balloon is a set of CPUs. So every balloon has some set of CPUs and those are configurable. For example, this balloon has 2 cores, this balloon has, I don't know, maybe 7 or 8. And the other one has 4 CPU cores. And the same case that we had 16 cores, and we could also leave one of these CPU cores for just on the system so that none of the balloons is touching it. That's also possible. These balloons can shrink, so basically they can inflate or deflate. Inflation means you add more CPUs to the balloon, and deflation means you remove the CPUs from the balloon. It's not you actually, it's automatically done, but of course you can also tune those parameters. So we created balloon. What do we do with that? So balloon is basically a representation of some piece of CPUs. Then when you're placing your workload on the Kubernetes, now you have to tell it, hey, I want my workload to be running, for example, on this CPU, on this balloon. Why? Because maybe there's something important on this course. Maybe these cores are isolated, kernel isolated CPUs, or maybe these cores have some better frequency, or maybe these cores are, I don't know, close to some memory unit, or maybe these cores are close to some other device on the hardware. So you can basically tell to your workload to be running on some specific balloon. The way to tell is that you could, of course, use the namespacing, saying that on the balloons configuration, you can say that if there's any workload or if there's any pod that is created, for example, in namespace A, please run that or create those containers within this balloon. Or you could do it from the vice versa, basically saying from the pod spec or the metadata, putting some annotations that will actually try to find the balloon that you're requesting and then attach itself to that specific balloon. There are some links which are small and you don't need to take the pictures. So basically we have this, I earlier said that we have this plugins collection repository where we have at least 6 or 8 different plugins doing different jobs, different algorithms. The way that you deploy in general plugins nowadays is pretty easy. So you use the Helm, and then there's also an operator. So if you are about to use Kubernetes operator, then we created also operator that will install any of these plugins available in this repository. But then moving on, let's say we have this balloon that has eight CPU cores. As I said, balloon has a set of CPUs. It can inflate and deflate. One single core or logical CPU can be part of only one balloon at a time. You cannot use one core in 2 different balloons. And balloon is a means of your CPU and memory preferences. So when you're creating the balloon, you as a cluster administrator can say that how do you want, or what kind of workload you want to run on this balloon. Not every CPU has to be part of the balloon, so you could exclude some of the CPU cores on your host. Then how do we configure the balloon? So it's a CRD, normal standard procedure in Kubernetes. So we have a CRD called balloons policy, and from that you can basically express your preferences about the balloon or balloons, because single balloons policy is used to create bunch of balloons. So it's kind of like a replica set, but not the same, because replica set has the same parameters for every pod, but in this case these are different, but it's a list basically. It's a 0 config by default, but doesn't mean that you're not allowed to tune. There are a lot of things you can tune. Some of the configuration options that I just wanted to highlight is, for example, you can say how many minimum CPUs or how many maximum CPU cores should be in a balloon. So there is a field called max CPUs, min CPUs. You can specify the minimum frequency or maximum frequency for the balloon. So it will actually go and tune frequency of your CPUs that are attached to the specific balloon, for example. You can also say that, hey, I want this balloon to be close to some specific devices on the host. It could be some PCI device, or it could be some, I don't know, some memory or some other devices on the host. Then you can also say that this balloon, whenever, for example, it's inflating, it should try to inflate in such a way that it should use the CPUs closer, for example, closer to each other. For example, first it will try from like we saw in the tree earlier, if I go back, so here. So first you can say that try to get some CPU cores from the same die. If you don't find any CPU cores in the die, or if there's no empty, then move on to the socket level, because in the socket level, there's a high chance that there is another die. So then it checks on the same socket, so you have 2 dies, meaning you have 4 cores. And if it realizes that there is no more core left even on the same socket, then it moves on to the next socket. So meaning you have the whole system access now. So it basically tries to tie the cores closer to each other, again for the same reason that it's faster for the CPUs to access the memory. So yeah, then you can also say there's an option that we added recently. You can say that I want for this balloon only isolated CPUs. So in the kernel you have these isol CPUs. So you can basically, for example, out of 16 cores on your host, you can isolate some of those cores from the kernel scheduler, and Linux scheduler will basically won't touch those cores. But then if you want to use them still, you can use this with the balloons option, saying that, hey, I want, or I prefer isolated CPUs. It's a preference, it's not guaranteed. So because there's a chance that there are no isolated CPUs on the host, or maybe there's not enough isolated CPUs on the host. So when you're saying prefer isol CPUs, balloons policy will try its best to match your request, try to find the isolated CPUs, and then assign those CPUs to your balloon. And then when you're placing your workload on that balloon, then your workload is fully isolated, not only on the Kubernetes or level, but also on the kernel level. Because scheduler is not touching that. I mean, Linux scheduler. Then there is another field called available resources. With this field, you can say that out of 16, I want to use only 14, because for the 2 cores, for example, I want to reserve for the kubesystem namespace, because kubesystem is our Kubernetes, so I want to make sure that my API, controller manager, all those critical pods are up and running. So with the reserved, you say which CPU set you want to isolate or like reserve, and with available, you basically tell whatever is allowed to be used for this balloon. Then there's also allocation priority. So priority is used when you have multiple balloons. So for each balloon, you can put the priority saying high, normal, low, or none. And then when there are different or similar balloons, and then when there's a request to be inflated for 2 similar balloons at the same time, then this priority will take place, or like balloons plugin will try to inflate the balloon that has a higher priority first. And there are more. This is just like a small subset of the configurations, and so I didn't want to cover everything because we have limited of time. Now I will try to switch back to the demo. And in this demo, I will just quickly talk what I'm going to show. Let me clear up this. So I have Kubernetes local cluster running on containerd. If the text is too small, let me know. So we have a single node cluster that is running on containerd 1.7 version, which has the NRI, and I have enabled NRI. Oh, by the way, I earlier said that NRI is not enabled in these versions of the containerd and CRI-O, but when you're installing the Helm chart, or when you're installing the balloons plugins or any other plugin with the Helm chart, we have the flag, so you can say that enable NRI. So there is an init container that spins up. Init container first enables the NRI and then deploys your plugin. So you don't have to go to every single node. For example, if you have 10 nodes, you don't have to go and SSH or use some other tooling to enable NRI. So Helm chart will actually take care of the enabling the NRI on every node. So this is a single node, and I'm using my host. I have 16 cores on this laptop, and all of those cores are exposed or available for the Kubernetes. Out of these 16, what I've did is that I, just a moment. Yeah, I have isolated 4 of my cores, starting from the 12 to 15. So these are isolated from the Linux. So Linux scheduler will not touch those. But my idea is that we will try to use the balloons configuration and try to use this specific isolated CPUs for our workload, and assume that our workload is super critical, that we want to use the Linux level isolated CPUs. Then the second part of the demo would be about configuring frequency. So I said that with the balloons, you can actually tune the frequency of your cores. But to show that, so I'm gonna use this stop. Let me do a little bit of configuration because the coloring is not good. sorry. So now, so I will click here so that we see the frequency. So now you can see the frequency, and you see that we have 16 cores. Out of 16, these 4 guys are isolated. So that's why you see that they're fixed frequency. Nobody's touching that, nobody's using that. I mean, Linux is not using that. All the CPUs getting used from 0 to 11. So we will try to tune that frequency as well, and we will try to use those CPU cores for our workload. So for the workload, I tried to come up with something, but then the easiest was that I'm gonna use the KubeVirt. So the KubeVirt is the CNCF, I think sandbox project, if I'm not wrong, or maybe incubating. So in short, KubeVirt is basically creating virtual machines within the Kubernetes. So as my workload, I will just create one pod, which is essentially a virtual machine. So inside the pod, there's a virtual machine, and then for that pod, I will try to assign only those specific CPUs through the balloons configuration. So the KubeVirt is already installed. I'll just quickly show that. So you can see the KubeVirt namespace. There are a bunch of pods. We don't have to go into details. This is not the main topic, but balloons policy is not installed yet. So the first thing that we're gonna do is that install the Helm chart, and I'm gonna use the local Helm chart because there were some changes that I made which are not yet in our public images. So I'll just use the local Helm chart, and the image is already available in my registry. That's why it's gonna start very quickly. So, and if we just keep watching the containers, we should see in the kube system namespace this pod. So this pod is basically our balloons policy, or like a controller. So the policy is running. What it did at the same time is that by default, I say that balloons policy is 0 configuration. It created the CRD, or the CR instance rather, with some default configurations. So we could see what are the configurations that it used. So we have the policy called default in the kube system namespace. I didn't create it. It's a plugin that created it. And so what we have here is a bunch of configurations. So basically, if you look here, there's the balloons type, which is the most important part. So in balloons type, this is the list. So you can, within this list, you can specify the CPU, the balloons configuration. In this case, I have 2 entries. So the first balloon is called isol CPUs, and the second balloon is the default balloon. So for this particular balloon, what I'm specifying is that I'm saying allocation priority high. So if there is a fight between 2 balloons, so this will win because the other one is normal. Then minimum balloons 1, so you can actually create multiple balloons on the same time. Then I'm saying minimum CPUs on this balloon is 1. And then I'm also saying that use this balloon to host the containers or the pods which are created on the namespace called isol CPUs. So whatever pod I'm creating on isol CPUs will end up on this balloon. And then, yeah, that's it. And then another option also I specified here is saying prefer isol CPUs. I'm saying that if there's a pod that is created in isol CPUs, so it ends up on this balloon should be using isolated CPUs on the host. So we have 4 isolated CPUs, and we should see that this balloon is actually using those CPUs. And the second, the balloon is default, but we don't have to go into details. It's actually talking about default namespaces. Isolated CPUs is false, so it's not going to touch it. So now, balloons policy is up and running, configuration is there. This is dynamic, so you can actually, it's mutable. You can modify the configuration on the fly. But now we need a workload. So as a workload, I say that I'm going to use the KubeVirt, and I'm going to basically create a virtual machine CR. What it does is basically it's going to create the virtual machine, but within a pod. So it will create a pod. Inside that, it will end up creating virtual machine. And then on resources, I'm saying that, hey, create two cores for this virtual machine, and then below I have specified also the memory amount, which is 4 gig. So now if I apply this, it should create a pod. Oops. I don't remember what was the instance. Okay, ISO CPUs, yeah. So the pod is pending. The reason is there is one label that I need to set, or not a label, actually the taint, because it's a single node. So I have to untaint. Well, taint is not there. The other thing is there is a label. Yeah. So now that label is related to Kubernetes, so we don't have to focus on that. So basically what Kubernetes is saying, hey, your pod is running, so it has 3 containers, so meaning my virtual machine should be ready. So how do I access my virtual machine? So first I need to get its IP address. There's a resource called VMI, or virtual machine instance, and that is the IP address. Now I'll try to SSH this VM. And it is using Ubuntu. I have specified here the Ubuntu image, disk image, and I will use the SSH. So SSH key was already provided as a secret, but again, this is related to Kubernetes. Just don't focus on that, but I'll just use the key that I attached to this host. Yeah. Okay, so we're inside the virtual machine. If you remember, we specified it should have 2 cores. Let's check the cores. So we have 2 cores. Then let's check the memory. That's interesting. Yeah, so it's saying 3 gig, but it's actually 4 gigs because we specified it at the 4 gigs. I don't know if you can see, it's very low. So now what's interesting for us is that, is it actually using the isolated CPUs? Because the pod that we created, it's actually on the, the pod that we created, it's in the ISO CPU namespace. So, and we say that we created a balloon. In the balloon we say if there's a pod that is in the ISO CPUs, please use the isolated kernel CPUs. So how do we check that? We have the metrics that comes with the balloons policy, and I have enabled it. It's not enabled by default, but I already turned it on. So now I will just go and check the metrics, and here try to find the balloon. This is the Prometheus data. Just a second. It's a bit hard for me. Oh yeah, there we go. So what it's saying is that this is balloon called ISO CPUs that is currently running the pod or the container that is named like this, which is our virtual the Kubernetes VMs pods. And it's also saying that, hey, I'm using the CPUs starting from 12 to 14. And if you remember, those CPUs were isolated CPUs. So here. The another way to check is that, okay, how do we know really, like, sure, we have the Prometheus, but let's create some stress inside this virtual machine, and we can see if the CPU usage goes up on those CPU cores. So what I will do is that I will basically SSH back to the VM, then quickly install stress utility, and then generate some stress, and then we should see it jumping here. At the same time, I have a Grafana actually here, which is monitoring that node, and we will see if the CPU usage goes up. Right now it's saying I'm using 1.4 or 1.24 cores, which is nothing but, okay. So you can see that 12, 13, and 14, they are almost empty. There is some usage, but it's very low. Now I will just stress this virtual machine, which is supposed to use those CPU cores. And you can see that the CPU usage jumps to 100% because we're just generating some load here. The other thing, actually, well, I will show you later. So this is how balloons basically ensure that it's using the isolated CPUs. The other thing I wanted to show is the CPU tuning. For the CPU tuning, I don't know if I have time, maybe 2-3 minutes, if it's not late. So the other thing is that in the balloons configuration, you can, this is just one example, you have this class. So when you're creating the balloon, you can actually say that this balloon is part of particular class. And once you say the class, you have to specify what that class means and what can you do with that class. So one of the things that you can do with the class, for example, saying that for this class, we have the frequency that is maximum this amount and then the minimum is this amount. So right now, if you look at the frequency, it is roughly 400 megahertz, but let's try to modify it with the balloons configuration. So for that, actually I have to redeploy the balloons policy because I need to change the frequency there. Let me do that quickly. So I will just enable it here. Instead of 400, I will maybe put, this is gonna be 1100 megahertz. So, because here it's in kilohertz. So now, if I update this configuration, oh, this is actually part of the Helm. So only thing to save my time, I will redeploy the balance configuration because otherwise I need to modify the CRD or the CR. So let's do it quickly. I will delete the workload, which is this virtual machine, and at the same time I will also uninstall our Helm chart for the balloons. So Helm uninstall. So this is gone. Now the modification is done. So you can, before we actually do that, you can see the frequency is 400 megahertz for those 4 cores. But now when I apply the balloons configuration and when I actually create a workload that is using that balloons, then it will go and then tune that CPU, the frequency. So again, first let's start with the Helm installation of our plugin. So the plugin is installed. Now let's create the workload again. So the workload is there. Let's check the pods. So it's pending. Again, I have to set the label related to KubeVirt. Okay, it's initializing. So there's init containers. Soon we should see, oh, you see the frequency is changing? So this is actually balloons that is tuning the frequency. So it will set it minimum to 1100 megahertz right now. Previously it was 400. So this guy is not touched. Why? Because right now the virtual machine is requesting only 2 CPUs. So there is no need to consume the last isolated CPUs. But if I would try to push the balloon by creating some extra workload for that balloon and trying to inflate it, and then it will try to use the last CPU core, which is isolated, and then when it's touching that, it's also tuning the CPU frequency because that's what I specified in the balloons configuration. So yeah, that's pretty much it. Again, this is very limited set of the configuration options that you have, and we have some people in the community. This is the community work. It's like open source. It's not owned by Intel. It's container. I can actually quickly show that, maybe 1 minute more. So this is the project. It's under the containers, where you have some other bunch of containers related projects, and it's called NRI plugins. And you will see all the plugins, and we do the packaging and everything there. This is just like a source code. you can go and do whatever you want, of course. But then when it comes to installation, we have the help charts. You can find them on the Artifact Hub, but then also we have the operator that is installing all of the plugins, and then there's a extra CRD that lets you pick which plugin you want to use and do the parameterization and everything related to that. Yeah, thanks a lot for listening, and please, if you have any questions now or later, please don't hesitate to ask.
So I have two questions.
Yep.
My first question, maybe not really a question, but people could be carpooling, but if you give them the opportunity to have their own car, they will take their own car. Aren't you afraid that we create a scenario where now that people know that they can have their own CPU, they will be like, oh, why not? Even when they actually don't need it.
Yeah.
And my second point related to that is that it took a lot of time for people to understand how to set limit and request for the application, because they didn't have the observability to understand. I don't know how many memory I need. I don't know how many CPU I need. I have no idea, and we know how it works. Then just people guess.
Yeah.
How would you define some of the numbers that you show us? Like, how can I know how many CPU core I need? How could I know the rate I need and all of that? So what's your opinion on this?
Yeah, actually, like we had some, related to that discussion, we had some features that we actually wanted to extend these plugins even more so that you could actually go even deeper into the architecture and do very advanced tunings. But then right now, some of those pull requests are actually blocked just for the same reason, because we don't want to give the gun to the user and then just shoot on their food. So, and maybe one of the things that we as a community is seeking actually some feedback on this project, because we did quite a lot of feature implementations, but currently we're seeking for the feedback we want people to use. There are some projects and companies using that, but it's really hard to get the feedback and then understanding like how do you actually come up with some specific numbers or the ways of measure that this is like a best like setup. And probably there is no such a specific setup or the numbers, because every use case is different, every application is different, consumption is different. It's really hard, and of course using this also requires some clear understanding of your architecture. But it doesn't mean that you cannot run it on the cloud infrastructure, for example. It's not only for on-prem Kubernetes, you can also use it on the cloud. We have verified it on most of the cloud providers. If you're using in the cloud, in most of the cases they don't have multi-NUMA architecture. The virtual machines is like a single NUMA. So some of the plugins don't really make sense to use. But for example, these balloons, it has quite a bit of extra features to isolate the workloads for the avoiding nosy neighbors. But then again, to answer your question, I don't know, to be honest. It's something that we have been thinking and had this question for a long time. I have actually my colleague Sasha or Alexander here. Maybe he wants to add something.
Yeah, I would like to add. So, in reality, balloons is one of the most complex and configuration policies what we have. It provides a lot of knobs what you can tune if you understand what you're doing. If you don't understand what you're doing, and it's also one of the use cases what we're trying to do, is what we are not asking you those numbers. What we're asking is like create the buckets or balloons or pools, whatever you call it, is what you just say, I want this application separated from this application, and this is the criteria how to separate. What policy does in background, it will create a balloon based on your request needs. So if you have like two applications in one namespace, like in one bucket, each one requires like 0.5 CPU and another has like 3.5, we will create a balloon which consists of 4 CPUs and let those applications run on this small pool. If you get another port, it will be inflated. So you don't need to specify any strict numbers unless you understand what you are doing.
So are those like priority flags or something like that that you can define to
Yeah.
different parts?
Yeah,
Okay.
so there are priorities, yeah. Any other questions?
So I love this. As a systems guy, I love exposing all the capabilities down to the nitty-gritty details. For me, it feels in a Kubernetes world as a team being told they need to do Kubernetes, but at the same time them having the requirements to like still pinpoint to hardware. So otherwise they wouldn't do this, but because they've been told you need to do Kubernetes, you still need to pin your workload to something, otherwise you don't really function anymore. That's why I would do this. But ideally, as someone who's consuming this, I would say, don't even put me on Kubernetes, because I need to manage my hardware at such a detailed level. Is that fair? That this is still mostly coming from that angle?
Sasha saying no?
No?
No. So
So the main point is what, like, remember the previous speaker, he was saying like, we want to run CPU, all our pods with CPUs 100% utilized. The question is, what is utilized for? Fighting for resources, fighting for the cache transfers, fighting for memory access, waiting, and so on. So what this allows you to do is actually group the workloads based on needs. So one of the biggest use cases what Balloons policy was originally created for was a separation of monitoring and logging infrastructure from the main workload. So you had the main workload which says, like, I will consume whatever CPU time you give me. But what happened next to your system? Like, your logging and monitoring starts to fail because we simply don't get the shares from the Linux scheduler. It just like fails for like liveness and readiness props. So what we can do, we can say, okay, we allocate one CPU core just for this like logging infrastructure pods, and nothing will consume the CPU time out of that. So your logging, your monitoring will be always working, regardless whatever like misbehaving main workload will be doing on. And this is just like one of examples. Second thing is what like optimizations for like different components on the system. So we have possibility to limit the burstability of applications. Like, of course, developers wants to put saying like, well, I want like my request is 1 CPU and limits either not specified or like 20. In reality, you can limit saying like, well, it might request 20, but well, it can set limit to 20, but real limit will be something like that. So for cluster admins, it gives a lot more flexibility on top of like normal Kubernetes resource management to make sure that the usage is utilized fairly in most of the scenarios. So it's not only about the hardware, it's more about the controlling the priority between applications.
That sounds more like I have infra and I have a workload, and infra is supposed to consume, let's say, up to 20% and keep my infra running. It sounds way simpler than what he's showing right now. I hope people just say infra uses 20% and not go all the way of managing CPU frequencies.
We are engineers talking to engineers.
Yeah, this is.
Sometimes.
You have users.
Yeah, like if I had a laptop that had like, or the machine that had, let's say, more than one NUMA, then I would show some other demos that would be maybe easier to consume and maybe not scare people. Actually, this is, as I said, this is very advanced configurations and doesn't necessarily require everyone or whoever is starting with the project to use, because as I said, it's a zero config initially, so when you're just deploying, you don't need anything. And I could show some benefits if I had some multi-NUMA node architectures, so you just don't touch the configuration, stay away from it, and it's you're already saving some CPUs and memory already.
I mean, where you really get some headlines with this, if you can pinpoint specific pods to some PCI complex. So your pod can go to their AI accelerator.
Yeah,
and
yeah,
that's where you
exactly.
get the funding.
Exactly. Yeah.
It's done
Yeah.
by default and in background.
Yes. Yeah. Out of the box. Yeah.
You don't need to worry about it. It's done automatically.
Yeah. Any other questions?
Yeah, thanks for the presentation. And my question is, will it work on IRM machines?
It should work. I didn't personally did any testing. Sasha, did we have any tests on our machines?
We haven't tested.
No. So can't really say.
It's supposed to work because nothing really architecture specific there. So whatever Linux kernel provides, we are using. But we haven't tested.
Any other questions? Okay, if you have more questions, you can just come and to me or to Sasha talk to about this. And yeah, thanks for listening.
And you can even drink, eat a burger.
Yes.
So,
Yes.
thanks for the presentation.
Thank you. Thank you. Thank you very much.
And let's immediately jump to quantum things.
I can do that. Thank you.
It's your choice.
My hand. Here. Oh, yes.
Should we wait for the?
Yeah, let's.
So does this work? Like the mic? Okay, now it should work. Yes. appreciate that most of you are still here on the seats in front, but the rest are welcome to join. So the talk will be about quantum computing and Kubernetes. And because in the quantum world, every project needs to have a queue in it. So that was easy for Kubernetes, so it's like Kubernetes. A bit about myself. So I'm quite new to the quantum world. So I joined University of Jyväskylä last year in May, and I'm kind of like an intruder there because my background is mainly in software. So I have been dealing with mobile phones, augmented reality, medical software, and then at University of Helsinki studying how to, let's say, reconcile regulations with software-intensive systems. So last year I joined this team called Quantum Information and Computation. Our sponsors, because the research wouldn't be possible without contributions from Business Finland and Academy of Finland. So our team is, let's say, a bit largish, like about, maybe now we are 12 people, and the composition is, our backgrounds are physicists, so we have people that do quantum computing on tape, on whiteboard. So they are working with matrices and this kind of theoretical concepts. We have people that they try to apply, so they design quantum algorithms, or they investigate quantum algorithms, and myself, I'm towards this like software or applied. We want to use like how it is used in practice, and we have there like the result of quantum computations. So when I joined the team, they told me that quantum computing is pretty easy. Like, it's like Python. You install Qiskit, so it's the first, like the most popular quantum development framework. So you have something that looks like Python. You execute it, and then you get a result. So this is the quantum circuit. So we have 2 qubits and the classic bit, and this would be the result. So we have a distribution here, like 1, 1, 0, 0. And yeah, this was pretty much it, like the crash course on quantum computing. And then I started to look at this, and there are some things that, how to say, they are a bit special, because I'm coming from the classical world where we are working with bits, and the bits can be either 0 or 1. So that's the only possibility. This is how it works. So on the quantum side, we have quantum bits or qubits, and a qubit can have any value, or as a representation, a qubit can have any value on the surface of this sphere. So it can have an infinity of values. And there are 2 ways to what is like the phase, and with 2 parameters you describe what is the value of the qubit, so the phase and the amplitude. But like a qubit that has any value doesn't have too much, or can have any value, is not of too much value. So the quantum computing is leveraging 2 properties of quantum mechanics. So one is superposition, and with superposition means that a qubit can have a probability half-half of being in 2 states. And here we have like either 0 or 1. And then the other characteristic of quantum mechanics is entanglement, which means that you can make 2 qubits to have the same state. So if we will have 2 qubits here, so it's either like we have a probability 50% to be 0, 0 or 1, 1. And these are the things that make quantum computing different and very weird if you are coming from the classical world, because instead of working with ones and zeros, you start to work with probabilities and this kind of entanglement, superpositions, entanglements, and yeah, things start to rotate here, and there are matrices and vectors, and you don't know where you are. Of course, another very interesting aspect of quantum computing is that you never know in which state these qubits are until you read them, and then the state collapses, and this is like makes it ephemeral. So there is no way to replicate. So you run again an experiment, but there is no way of going back or resume it, or when you program, do this kind of like debugging step by step. We don't have this concept, so this is again like something that makes the whole thing, let's say, complicated. And in terms of qubit implementation approaches, so we are at the beginning of this, like, how to say it, like technological revolution, and so far, let's say commercially, we have special purpose quantum computers. The most like successful company here is D-Wave, and they have something like 2,000 qubits, but you are not able to program them, so they are not general purpose. So they are used in this kind of like quantum annealing. So you can do computation on sparse matrices. So if you have a problem that is suitable for that kind of thing, you give it to this company and they will give you a result. And it's a bit of a magic, but this is how it works. Then general purpose quantum computing, so you basically are able to program and access every qubit and create entanglements between them, rotate them, or apply transformation, so basically doing the programming. And current, let's say, leading technology or is the superconducting, so IQM is making one computer like this, so this is a Finnish manufacturer. So I think this one is this is an annealing, this is a superconducting. So the processor is somewhere here at the bottom. It is enclosed in a cryogenic unit and is very close to zero, absolute zero. And at that temperature, you have this quantum property. So kind of expensive and difficult to scale up because there is limited space here inside the cryogenic unit. Then trapped ions. So these are particles trapped inside cavities. Photonic. So this is mostly I'm not so sure like how, but kind of like communications applications. And then electron spin. So this is or electron or particle spin. This is using, or the promise is to use the technology used for classical semiconductors to create dense circuits. So the most promising for scaling up will be like electron spin. The proponents of these ones are Intel and Semicon, another like Finnish startup. So in terms of like if we look at like quantum computing and classical, we are like, if somebody remembers what these are, like what is electronic cathode lamps, so very very, let's say, rudimentary work, not at that time. And then the circuits are pretty much, you program them, you pretty much need to wire everything there. So early stages of the technology, so we don't have yet like the equivalent of a transistor, and that makes this whole field interesting. So going back to like the first program. And because this is like I'm a software guy, computer guy, I wanted to see like what is happening, like 3 steps in Python, but what is actually happening. So that program is here. So you as a user, you develop a classic software system, and it has a quantum component. This quantum pipeline, whatever you want to call it, sends the circuit to a classical computer that is the control system of the actual computer. The information that is exchanged is quantum assembly, or an alternative which is quantum intermediate representation, which is based on LLVM like there are LLVM extensions for quantum instructions. And then so this is like here you program an ideal circuit, and then the classical computer has the job to map your ideal circuit to the actual qubits that are available and the connections that are available. So it will reroute your program to what is available on the computer, and a control system will send a sequence of pulses, and it will control the state of the. So this will be like laser pulses or microwave, depending on how it is. And so it will prepare the circuit for the quantum computer, and then it will measure it, and then you will get back the result. So quantum computers are actually quite expensive and very rare. So to make it simpler, you can run the quantum circuits in CPUs if you have smaller circuits. But if there are larger, so larger means like maybe larger than 20, you need a GPU, because then the time becomes too long. The quantum computers currently are quite noisy, and you can simulate the noise also if you have a GPU. The largest circuit that I managed to run was around 13 qubits, so it's like very tiny things. And then you can execute them on actual hardware. So there are available. IBM Quantum has quite a large collection, and so far they give some free quota, which is generous, but it will end next year. So it will be quite small, and then AWS, Azure, and Google, they all provide access to quantum computers via online notebooks. But the problem, or let's say you may wonder why we are here at Kubernetes. So we have quite a large variety of hardware here, and you want to access it in a let's say simpler way. And here comes how to use Kubernetes for quantum, or what would be the quantum components for Kubernetes. So, well, actually, before going there, so the way this works is like a batch system, because you need to connect to this classical computer. It takes some time to prepare the quantum computer. You run it several times because of the noise, and then you get back. So the time is short, but it's not as short as running some processes locally or whatever, in classical. So it looks like a batch. And in the quantum, or how to bring quantum world into Kubernetes. So obviously you have classic nodes that have CPU, GPUs, and then for we need to introduce another type of node that has quantum capabilities, and that needs to be advertised at node level. So you have some labels here and capacity and things like this. So this will allow the scheduler to schedule jobs. So for executing that program, I think that the most let's say obvious object in the Kubernetes world is the job, because you execute once and you get the result and that's it. So you finish. So we are quite, let's say, not very sophisticated. We use very basic features of Kubernetes, but the benefit of using Kubernetes here is that you as a user, you are hidden from everything that is under here, like the hardware variations or what kind of GPUs you need, and you don't have to manage all that thing. And this is like for my colleagues that are not as, like, let's say that they are either physicists or they design algorithms, so they are not that skilled into the whole stuff that is underneath that powers the computing infrastructure. This is a big problem. So how do you bring, or how do they get to use NVIDIA GPUs? These quantum simulations, they don't run typically on GPUs that you find in common hardware. So a normal laptop does not have that capability. So the containers, or the way we use containers is that, okay, we have the host and we have like the GPUs. In our test environment or lab, we have NVIDIA 4090, which is kind of okay. We have used also A100, and they are like with the 14 gigabytes of RAM, they are kind of similar with the 4090. So you have the drivers here, and then we build images. Or the way we use images, that we have a base image that has Python installed and the CUDA toolkit that matches the CUDA version that is on the host. And then we install also the CUDA and this CUDA for quantum extensions, so that they all match what is available on the hardware. So you as a developer, you only need to install your own dependencies. And this would be like, make it as simple as you will develop on your own hardware. So using the CPU. There are some differences, but let's say in principle is this. And we end up in this situation where we have these Jupyter users, because the physicists and the algorithm developers are not, they don't make Python packages or anything like that, so they work with Jupyter notebooks. So in order to use this system, we have developed a custom Jupyter kernel, and this kernel takes this, when you execute a cell in the notebook, it takes the code, it packages it in a job, creates the secrets that are needed if you have an environment, a config map, so that you don't have to rebuild the image all the time, sends it to the cluster, executes it, and gets back the result. And this would be the demo. So, wait a minute. So we are here in the demo. Okay. So what I will do now, I will start Jupyter Lab with the kubeconfig that points to our cluster. Okay, it started. It takes a while, so Python is kind of slow. And now I'm having here the same, okay, you can see there. So I'm having here in a Jupyter cell the same, the code that I showed in the beginning. So this is the hello world. I have some other more complicated, so this is enough. So when I'm so this is, so the kernel looks the same as the standard kernel. it is, let's say, pretty easy for these guys to work with. Okay, so it connected to the kernel, and now when I'm executing this cell, what is happening is that, so the job was created, the config map that contains the code was added to the cluster, then we have the environment, so these are environment variables, and then the pod was pending, running, and we get the result here. So here is one environment variable, so I'm using it for test. So the distribution is, I'm running it 4,000 times, and I get this distribution. I think that if I run it again, it will, it will be in this cell. So it will change. Yes, there is some other distribution. So the value here is that, okay, although the system behind is Kubernetes, so jobs, these config maps, secrets for the environment variables, the user doesn't see anything. So they can do their work as they would do it locally. They can even switch to the local environment. So if you select the Python kernel here, you could probably run it locally, but this is with the GPU. I don't know, like, if I put a CPU here and maybe it runs, maybe it doesn't. Okay, it will not run. Yeah, I haven't installed something there in my local machine. So back here, so this is like, you may wonder, like, why running these quantum jobs on Kubernetes? Isn't it like the Starship there or the Death Star? Maybe it's too complicated. So that as I said, we are still in the early stages of quantum computing. So this is called like noisy intermediate state quantum state or phase era. Yeah. And we are about, so here it is like mainly experimentation with hardware. So 7 years ago there were no hardware qubits. So it is a very, very like new discipline and quite like tied to the lab. And this is also like why everything happens in Python notebooks and so on. So we are on the verge of moving into, this is called quantum error correction. So the manufacturers of these quantum computers, they try to fix these errors in hardware. So they want to expose or to build out of physical qubits that are like what we have here, logical qubits, so that what you program is what you run. So you will be able, like, that kind of like rerouting and mapping to the hardware to not become a problem all the way to the user. And that phase probably will, I mean, here is an estimation, it will take like 10 years, but somehow in the middle or maybe in the first years, we will see the first practical results, or not results, application of quantum computing. So right now, so IQM has a 50, or they announced a 50 qubit computer. If the largest supercomputers like Lumi can simulate up to 43, 44 maybe qubits. So that requires quite a lot of power. So when, like, maybe next year when this 50 qubit will be available, we will be able to make a lot of like more ambitious experiments. So go further than this, like, does the qubit work, or can I do quantum teleportation, or these kind of simple things. And then after the like in 10-year horizon, so we will be into this quantum error correction advantage, and that advantage means that quantum computers will provide better results than classical alternatives. And of course, like the holy grail is like fault-tolerant quantum computers, and there is when this RSA encryption breaking will happen. So although we hear quite a lot of these things in the news, they are quite far in the future. So those require like millions of qubits, so we are not there yet. But this is like we learn and we experiment, and this is what takes the field further. And you can send me emails if you want about this, like ask questions. We have something about Kubernetes on this website, and the kernel is available on GitHub. The talks is like towards reliable quantum software. We need to have like fancy names like in academia for these projects. And this is it. Hope that it was the last session, but not we are still around for some questions here.
Any questions? I would have a question if nobody else. Does it in this roadmap kind of thing? You showed that next year something will happen.
Yes, we have promises.
We are already late.
Sorry?
Will it happen or we are already late?
I don't know, like if we are late. I think that so the first, like if you look at the timeline of quantum computing, or the first, like quantum mechanics was discovered in the late 19th century. Let's say quantum information technology or the qubit concept, mid 20th century. The first algorithm was like 1991 or 4, if I remember correctly. First computer 7 years ago. Now we are going into 50. I think that, I don't know if this is like a hockey stick, but definitely it is accelerating. So, and there are at least IBM is like talking about 1,000 qubits, but because they are they are noisy, and if you use the whole computer is so noisy that the accuracy is like, or fidelity is 0. So that's the thing. Like so not the number of qubits is important now, but improving the fidelity of them. So the error correction, so that they can be used more easily, and take the technology from the deep lab into the open, so that it can be used in practice by people that are not physicists or mathematicians. And this is I think that's the most important, not the qubit count. Or yeah.
Thank you. Any other questions?
I'm Vlad. We both have a common thing. I'm from Jyväskylä also, and I worked in Nokia. So the thing is, like, I mean, looking at when people start investing physical money and like really putting the resources, what are the gut feeling or the projections that which are the industries are going to embrace quantum computing, so that like they, I mean, the size of the transactions, I don't know how you quantify that one.
Yes, so there are. So if you look or if you read the news or the blogosphere, I think that there is a lot of talk about post-quantum cryptography. So because the quantum algorithms are very good at factorizing prime numbers. So you hear about encryption breaking, but in reality, I think that the first use of quantum computers will come into, let's say, more mundane domains like optimizations. So logistics, this traveling salesman, so reconciling conflicting, let's say, problems. That would be the first one, and I think that there are quite a lot of methods to solve these kind of problems with classical methods, and so sometimes in here, you like silently, quantum computers will lurk into, like, and they will replace these classical systems when they will be ready to provide better results. So I think that it will be like, this is my feeling, it will be like a silent, like, march towards this kind of like more spectacular applications. But yeah, that would be like my prediction. Did I answer the question?
Yeah, I got it. Thank you.
So was this more of a tech demo? How would I do quantum in Kubernetes? Or is this, you mentioned IBM and Microsoft, are they actually looking into exposing quantum infrastructure in their Kubernetes environments? And it's a real current problem to solve?
So currently, let's say the dominant view in the, well, not dominant. So quantum computers are used together with in HPC environments, so high performance. And this is driving the development because they are accelerating, or they are accelerating computations in that kind of problems that are used currently for this kind of simulations. However, there is a general trend to align cloud native with HPC. So last year, Linux Foundation announced the formation of High Performance Software Foundation, I think it is. So it is like a parallel to CNCF, and the objective is to cross-pollinate so that you can take or align the stack so that you don't duplicate solutions. And I think that it is already recognized that HPC does not have like the monitoring and the scheduling capabilities that are available in Kubernetes. So at some point, this will become part of HPC, and it is kind of ironic that quantum computers are currently like seen as part of HPC environments, because HPC environments are like highly packed, like with interconnects. But at least like I think that most quantum computers are. So if you look at them, they look like that, and they have a web API here or an HTTP API. So they look much more like cloud native than HPC. So there is no memory interconnect here. So there is a network interface, and
there's no need for high bandwidth in between.
There is because yeah, okay. There are a lot of measurements that you need to know, like the way back. So you send a tiny part, but you get gigabytes back from the machine here, because you need to know how it works. Of course, you don't get it currently if you are like an IBM quantum user, so you will not get it. But if you are like IQM, and yeah, we are working with VTT and CSC, and I mean, we get to know like what kind of data volumes are there. But I think the idea is that it looks more like cloud than HPC, this quantum computer. And that's like, and what I want to say is that, so because this is so much like government driven, because it's in an early stage, and EU has a Euro HPC consortium, or I don't know what is the name now, this kind of like legal framework. And currently, like in the last what is the memorandum or something. So the plan for 2025 is to start working on an interface here that is called Universal Quantum Access, and that will allow both local and remote access to any quantum computer. So because manufacturers, they have their own APIs here, and they look very weird because they are done by physicists, not by IT people. So it is like, if you look at quantum and classical, so you have these 70 years of classical computing and mistakes and fixes and so on. So they need to be transferred there, otherwise they will repeat.
Thank you. However, I'm not sure if the APIs would be better if software people are doing them, but anyway. Thank you very much.
Oh, thank you.
Thank you. All right, then the next thing to do is to drink some beer, eat more hamburgers, and talk about stuff. And again, thanks for our hosts.
So do you actually get to use the VTT's quantum computer through Lumi?
Yes.
Okay, that's what I...